All right, today we're going to look at all the content as best I can and as short as I can, less than one full period today with advisory scheduling of our Unit 2, okay, as we prepare for this review. Now, Unit 2, we basically are focusing on exponential functions and logarithmic functions. But before I get there, this lesson started with kind of the leading into what is exponential, what is logarithm, and we define those based off table values that are arithmetic or geometric. So we started there with these words arithmetic or geometric. You may remember a linear function we learned in lesson 2.2 is the same thing as an arithmetic sequence. Now, in algebra 1, what was the formula for a line that you learned in algebra 1 that everybody has memorized? What's the equation? Y equals mx plus b. That will not do you that much good in my class because we're not ever going to give you the slope and the y-intercept. What we will do is we will find a rock. What does a rock represent? Do you remember?
The change of y over the change of x.
It is the change of y over change of x, but what in the equation represents the a rock? The slope, yeah. We will be given a rock and a point, and so instead we're going to use what's called point slope. We're going to use this formula, that y equals m parentheses x minus x1 plus y1. You need to remember this formula. Anytime you're dealing with a linear or arithmetic, you need to use this formula right there, okay? x1, y1 is a point. x1, y1 is a point. x1, comma, y1, this is a data point or a coordinate point. And this, again, is the a rock. That's how you will use that on the test, okay? So you need to make sure you have this formula. Now, as we jump down into exponential, the same can be said. There's a formula that you see all the time, but it's not necessarily the most helpful formula. For exponential functions or geometric, the formula you'll see given to you all the time is y equals abx. I'm going to start to slide down a little bit. But just like linear, this will rarely do you that much good by itself because we're going to have some transformations. And so the formula that would help you in my class is actually this. Y equals, does anybody remember what we changed that a to become? y1 times the base to the power of x minus x1. Once again, the y1 and the x1 are a point. X's are always liars. There we go. These are, again, a point. The x's are always liars. If it's helpful, I could put this in parentheses just so you can see that these formulas are very similar. But over here, that's an a rock. Over here, what do we call the b? What does b stand for? The base. The base. And that's the amount it's multiplying by. Okay, so notice these formulas are very similar in that the two formulas you need to know, for a linear, you'll have an m, which represents the a rock. And for exponential, you'll have a b, which represents base. X minus x1 will be in parentheses on both of these formulas. On linear, you add the y1. On exponential, you multiply the y1. Okay? That's your two formulas. Make sure you have those down. Those will help you dramatically on the exam, knowing those two formulas. Okay? Am I good to move on? Okay, so first, that's the formulas we're going to use for exponential and linear. Now, let's start talking about what these graphs look like. What is this graph right here? Is this a linear graph? No, it's not a line. It's a curve, so it can't be linear. What type of function is this shown right here? This is exponential. This is exponential. Exponential will always look like what I call an airplane taking off the runway, or it could look like an airplane landing on the runway, or if it's underneath the y-axis, it could look like a submarine coming up to the top of the water or diving down under the water. Okay, here. Okay, this is exponential. Now, second question, is this growth or decay?
Growth.
Now, it is growth. Why is it growth? It's increasing. As we go left to right, it's increasing. Now, on this problem, not only are we going to do that, we're going to discuss asymptotes and end behavior because you'll need to know those. So an asymptote is when the graph approaches a numerical value other than infinity. An asymptote exists whenever the graph approaches some numerical value, doesn't matter if it's an x or a y, that's not a positive or negative infinity. Does this graph approach any value in particular that's not a positive or negative infinity?
Yes.
Yes, it does. Where?
0.
0, absolutely. I'm going to go ahead and add that. And I would suggest you do as well on your packet. Right here, this part of the graph is approaching, that's not what I was wanting a dashed line. How about this one? Let me just change colors. This graph right here is approaching a horizontal asymptote. Horizontal means left and right. It's approaching a horizontal asymptote. So this is a horizontal asymptote the graph is approaching, and the reason it's approaching a horizontal asymptote is it's going to a numerical value. That is a horizontal asymptote because it's left and right. Now, what value is it approaching here? Like what? It's going to be a y value. What y value is this dashed line on? 0. It's y equals 0. That's your equation. Because that horizontal line crosses the y-axis at 0. The x's are changing. If you look down, this is like an x-axis. The x values are changing, but the y value is not changing. It's 0. It approaches 0. Now, if you have a horizontal asymptote, that will automatically have to be one of the answers to a limit or the end behavior. So now remind me, end behavior, this means limits. A limit doesn't tell you where the graph, finish the statement. A limit doesn't tell you where the graph is. What does it tell you? Where it's going. How many times is this graph going somewhere? Twice. We're going to write 2 limits. We'll write a limit for here. I'll do 1 for limit 1, and I'll do 2 for limit 2. Okay? Limit 1. You write LIM. This function's called f. You could do f equals. You could do f of x equals. I'll do f of x because that's the more proper way, with an x arrow underneath. Tell me, as this graph travels to the left, or as it travels to this arrow with a 1, what x value are we approaching? Think of x values. You're looking at the x-axis. That x arrow does not go to 0. 0 on the x-axis is right here. What's that arrow going to on the x-axis? Negative infinity. Now, here's where the horizontal asymptote comes in. You see how that says y equals 0? This arrow is approaching what y value? Is it? Here's the question. Is it rising? Is it falling? Is it getting really, really flat? Or is it stopping at a point? It's getting flat. What y value is it getting flat on?
0.
0. That's a horizontal asymptote will always come with a limit with that value placed in. Okay, and there's a second limit up here. The graph is going somewhere else as well. Now this arrow is not approaching any one numerical value. It's moving further and further right, and it's moving further and further up. So let's start with the x value. If it's moving further and further right, like it's not going perfectly vertical, it's still angled, what x value ultimately is it going to approach? Infinity. And what y value is it approaching? Is it rising, falling, getting flat, or stopping at a point? It's rising. And so those would be your 2 limits. Notice a horizontal asymptote, that value will be plugged in to one of the limits. All right, let's look at the second one. This time, I'm going to start a little differently this time. Tell me about my asymptote. Does this graph have an asymptote?
Yes.
Is there a numerical value our graph approaches that's not infinity somewhere? Yeah, which numerical value does this graph approach?
1.
It approaches a value of 1. Now, next question that's really, really important to get credit. Is it an x value of 1 or a y value of 1 right there? That's an x value of 1. This is not a horizontal asymptote. This would be called a vertical asymptote. Now, if your graph has a vertical asymptote, that is not a runway. Remember how I started last problem and I said that an exponential function is like an airplane taking off a runway or a submarine coming up to the water or diving under. The water and the runway represent the asymptotes. Have you ever seen a runway that goes straight up and down? Have you ever seen a wall of water that's straight up and down? No, this is not exponential. Exponentials have horizontal asymptotes. If we're dealing with the vertical asymptote, we're dealing with its inverse. What's the inverse of a exponential? This is a logarithmic function. Now, next question, is this logarithmic growth or decay?
Decay.
It is logarithmic decay. Why is it logarithmic decay? How do you know?
Concave.
It's decreasing. Now, what's tricky on logarithms, remember they're backwards. If it's decaying, it's actually concave up. Which way is this ultimately curving? Is it curving further and further down, or is it starting to curve more and more up? More and more up. Logarithms are backwards. So exponentials, if they're increasing, they're concave up. If they're decreasing, they're concave down. That's true on exponentials. This is concave up. If it was decay, it'd be concave down. Logarithms, though, are backwards. If it's decaying, it's actually concave up. Let's just go ahead and write that on there. This one is concave up. This next one is concave up as well. So logarithms are backwards in that regard. A decay is still concave up. Okay, we have the vertical asymptote. Now let's talk about limits. How many limits will this logarithm have? 2. Let's do that one first and this one second. Okay, tell me about my first limit. I call this one G. This graph, notice it has the G next to it. What x value is this arrow approaching? Very good, 1. Now, if your x value is a number, you have to put a plus or minus, indicating if you're on the left side of the graph, or left side of that number, or the right side of that number. This graph, is it on the left side of the blue dashed line or the right side? Nope, it's not. This is the minus side. This is the plus side. Which side is the graph on? The right side. It needs to be a 1 plus. Now, what is happening to my y's as I approach 1 from the right side? Is the graph rising, falling, getting flat, or stopping at a point? It's not falling as you go to 1. As you're going to 1, it's rising to infinity. That arrow represents a y value of infinity. Okay, now let's talk about the second limit. Limit g of x equals x arrow. That part is standard. You always have that on every single limit. Okay, what's happening on this time? Are we approaching any one numerical value? No, so it's going to be infinities. Tell me about the x. As you go to, this is pointing right. What is x going to as you go right? Okay, and it's facing somewhat downward. It's angled a little bit down. So what's the y value it's going to approach? Negative infinity. It's falling. Ultimately, this graph is falling over time. Negative infinity. Okay? Now, I think I have either 1 or 2 more of these. I think it's 2 more. Let's see what you can tell me first. Start off with asymptotes. What can you tell me on this one? It's a horizontal asymptote. Is this a dashed line? No. It's a horizontal asymptote at what value? Very good. It's y equals because it's crossing the y-axis at 2. Okay, this is it. Now, tell me if you've learned anything here. What type of function would this be? You could think of it as a runway or you could think of it as the water. Either way, what type of function is it? Nope, logs don't have runways in water. Exponentials have runways in water. This is exponential. Is it increasing or decreasing? Therefore, this is exponential growth. Let me think, what else do I want to say on this? Oh, limits. How many? Oh, nope. Concave up, concave down. Ultimately, which way is this curving? Curving down. And if you remember unbreakable chain, if it's concave down, that means its rate of change is decreasing and its delta A rock is negative. That's what that means. Its rate of change is decreasing. If it functions concave down, its rate of change is decreasing. Its delta A rock is negative. Okay, let's write our 2 limits. We'll call this limit 1. This will be limit 2. Tell me about limit 1. Is this limit, this is called h here. Is this approaching any numerical value or are they going to be infinities? They're both going to be infinities. Let's make sure we're correct on this. Which way, think of the x-axis here. Which way is this pointing as far as x goes, left or right? Left. So if you're going left, x is approaching what value? Negative infinity. Good. Okay, now tell me about the y's. So as you're moving towards that arrow, is the graph rising, falling, getting flat, or stopping at a point? Falling. That means it's pointing down. It's falling. It's falling to negative infinity. So ugly. Let me try this again. Goodness, I cannot do this to save my life. There we go. Okay. Let's talk about the second limit. The second time this graph is going somewhere. Okay, is this approaching a numerical value? Yes. We already said up here, is the numerical value an x value or y value? All right, go ahead and put that in there. It's an H. Just making sure you're following along. Great job. Y'all passed the test. Can't fool y'all. Okay. Jokes aside. Which way is my x pointing? It's pointing to positive infinity. Very good. Okay, just to make sure you thoroughly know this, I'm going to give you one more. Okay, tell me about function k here. Does it have an asymptote?
Yes.
Yeah. It does have an asymptote. Which direction, vertical or horizontal, is this asymptote? We have a vertical asymptote. So if it's a vertical asymptote, what type of function must this be? This is a log. Logs have vertical asymptotes. So if this has a vertical asymptote, which axis are we cutting through right there? The x. And this is tricky because that point, this is -4 right there. If that's -4, then what's this asymptote actually at? X equals -5. Good. That's a vertical
Concave
asymptote.
up.
It is concave up. No, it's not concave up. It's concave. It's not curving more and more up. It's curving more and more down. Logs are tricky. This is concave down because it is a logarithmic growth or decay? Growth. Logs seem backwards on their concavity. If it's a log growth, it's concave down. If it's a log k, it's concave up. They're backwards. This is concave down. Okay, how many limits will this have? 2. Good. Let's do the easier one first here. What value do we know this limit, this is called k here. What value do we know this graph, this limit is approaching? X or a y value? We know it's approaching an x value. What's the x value we know? Okay, if you're ever plugging in an x value in on a limit, you have to do a plus or a minus. You have to. My rule. All right, which side of the graph is it on? The left side or the right side? No, left is over here. This graph is not on the left side of that asymptote. It's on the right side, so it's a plus. -5 with the plus. It doesn't matter that it's going up or down. We're talking about the x value. X value doesn't go up and down. X value goes left or right. So you're asking yourself, which side of the graph is it on? The left side or the right side? We're on the right side. Okay, what happens on the right side as we approach that value of -5? It falls. If you're falling, where are you going? Negative infinity. Good. Now tell me about the second limit. Do we approach any value in particular, numerical value? No, so they're going to be infinities. What x value, which x value infinity? Positive or negative infinity? Positive infinity. And for the y, are we rising, falling? Rising, so it's infinity. Now, I don't know if you've realized there's a pattern here. And that's what our next question is going to be, if I'm not mistaken. Yes. There's a pattern here. I'm going to look at all 4 logs. How many numerical values do you see here on this log?
4.
Ignore infinity, sorry. How many actual numbers?
1.
How many constants? That's what I should say. How many constants? 1. Okay. How about this exponential? How many constants do you see? 1. How many constants do you see on this logarithm? 1. How many constants do you see on this exponential? 1. Notice exponentials and logs always have 1 constant value. If it's, think about this, if it's exponential, that means you have a horizontal asymptote, a y value. So your limit, one of the constant will be up there. Does that make sense how that works? Okay, if it's a log though, you have a vertical asymptote, which means that's an x value. Your x values will have the constants. Now you don't have to have that memorized, but I just want to point out that if it's a log or an exponential, how many constants do you expect in the limits? 1. Okay, so now come to this slide. It says, how will the end behavior of an exponential function always be described? Well, remember, exponential. Does exponential have a horizontal or vertical asymptote? Okay, since you have a horizontal asymptote, here's what I want you to think of. Since this has a horizontal asymptote, the horizontal asymptote, show me a horizontal line with your arm. Which axis would that cut through? This will generate some y value.
Did we give you already a blue box?
I don't have one.
Nope.
Thank you.
Any preference? Top, bottom?
Bottom. Perfect. Thank you. Okay, sorry about that. So if you have a horizontal y asymptote, exponentials have horizontal asymptotes. That means it's a y value. Your limits will always be like this. You'll have one limit. Why did I do that? Let's try this again. You'll have one limit. Actually, instead of saying f of x, I'm going to do a y, where the y will equal a constant. I'm going to do a as the constant, with the x going to a positive or negative infinity, and then you'll have a second limit where both values go to infinity. So notice up here, let me just put where a is a constant. Notice that if you have an exponential, you'll always have only one constant value, and it'll be one of the y values. Everything else is a positive or negative infinity. Are you tracking with what I'm writing here? Is this making sense to you? Okay, what's different on a log function?
That's a word one.
It has a vertical asymptote. So show me a vertical line with your arm. For vertical asymptotes, when you go to name them, you have to do it through the axis it crosses. That vertical line, what axis would that cross? This is going to cross the x-axis, therefore you're going to have an x value. So what will be different is your two limits will look like this. You'll have one limit where the x value approaches a constant, and your other limit where neither value is a constant. The one thing that's different, again, this is where a is a constant. The one thing that's different on limits is that if you're talking about the x value, you always have to do a plus or a minus. So up here, I'm just going to do a little minus, or a little plus minus right up there. You're either going to have a plus or a minus right there as well on that constant, meaning left side or the right side of the break. Logarithms is typically a plus. Are we good with that? Do you think you could determine graphs? You will have to do that on the test. You'll have to determine what type of graph it is. You'll have to be able to write limits. Was that enough examples to be able to do that? Feel good? Okay. Now let's transition into tables. So I've shown you visuals. We're now gonna, as in graphs, I'm now gonna look at tables, and then we'll go to equations after that. Now, let's look at this table. Looking at this table, you're gonna have to describe if it's exponential or logarithmic. Just like I did on the graph, we looked and we used different indicators. We were looking at asymptotes on a graph. If it comes to a table, you can't not use asymptotes because you don't know where the asymptote is. So we have to be able to determine a different way if it's exponential or logarithmic. What should we look at? You want to look at how it's changing. One should be arithmetic, one should be geometric. Okay, so let's look at this table. How much? We're going to do the delta y and delta x over here. Let's do delta y and let's do delta x. How are my x's changing here? Plus 2. And then how about here? Plus 6. And here? Plus 18. Okay, now let's do delta y. What's happening here? Plus 6. Plus 6. Okay, so we're adding the same amount every time. That means this is called arithmetic. That is arithmetic. Arithmetic is when you add the same amount. Delta y equals 6. Are we all on page there? Okay, are we adding the same amount here? This is geometric then. So I'm going to change colors here. This is geometric. Geometric does not mean you're adding by the same amount. What does it mean you're doing instead?
Adding two.
No. And we're not doing arithmetic of an arithmetic here because it would be like 2, 4, 6, 8 or something like that. But this is going from 2 to 6 and then 6 to 18. It's a different type of change. What's happening to these numbers? Go from 2 to 6 and then 6 to 18. You're multiplying. Geometric means you're multiplying. Here's how you find that value. You say b equals the delta x2 divided by delta x1. What is delta x2? Here's delta x. There's the first, there's the second. What's delta x2? Divided by, and I'll put the pluses here. What is 6 divided by 2? 3. Our base here is 3. This is geometric. Okay, if you're geometric in the x column and you're arithmetic in the y column, this is a log function. This is logarithmic. Logarithmic, by definition, the x's are geometric, whereas the y's are arithmetic. The x's will be one operation higher than the y's, no matter what property you're doing. Now, let's talk about if it's growth or decay. You need to look at the y values. Are the y values growing or are they decaying? Are they getting bigger or are they getting smaller?
Bigger.
That means it's logarithmic growth. Do you remember the rule? Is logs normal or are they backwards as far as concavity goes? So if it's log growth, guess what it is? Concave down. Which means its rate of change would be decreasing and its delta AROC would be negative. Go ahead. So I'll go ahead and put that. It's concave down. What's true about its AROC? Decreasing. I should have just been writing this down the whole time. And its delta AROC would be, this is called the unbreakable chain here. Negative. Morning. Okay. You ready for the next one? Oh, I'm supposed to write an equation. I'm sorry. I forgot to write the equation. If it's a log. If it's a log. The equation for a log, we have y equals, here's typically what you see. A times log base x. There could be some shift in there. Do I want to do, I'll do minus x1 here. Do I want to do that? I don't know if I want to do minus x1 or not. I can't remember if it has it. Let's find out. I'm going to leave it blank just for a moment. I'm just going to leave it open, parentheses, we'll come back. The a value is your delta y. Delta y is your a. A is equal to delta y, which means it's equal to 6. So in this case, our equation would be y equals, what's our a? 6 log, what's our base? 3. Okay, now let's do the math. Let's see if this works out. I can't remember if it does or not. If you plug in your first x, remember logs calculate the powers. If you plug in your first x, let's just do a little mental math here. If that was a 1, how many powers of 3 does it take to equal 1?
0.
What I'm doing is I'm plugging in 1. I want to make sure everybody understands what I'm doing. I'm going to erase this in a moment. I'm plugging in 1 to the logarithm. How many powers of 3 does it take to equal 1?
0.
0. What is 6 times 0? 0. Is that what it's supposed to be? Okay, that looks pretty good so far. I'm going to go ahead and close the parentheses. I think that's going to be our answer here. I think that's going to be my equation, but I'm going to test one more just to make sure. Okay, let's plug in the next number. The next x is 3. Let's try that. If I plugged in 3, what is log 3 of 3? I'm plugging that into this right here, this portion, the log. How many powers of 3 does it take to get to 3? That's what a log calculates powers. 1. What is 6 times 1? 6. Is that what it's supposed to be? Yeah, we got the right equation. Make sense on how to write that? Okay, so the delta y is your A, your base is obviously your base. All right, let's try another one. This time, what do you notice when you look at this table? They're adding by 1. So if delta x is 1, is this arithmetic or geometric? This is arithmetic. Okay, now I'm going to do delta y right here. How much is my y changing by? Now delta y means the change of that. How much am I adding by? It was 4. Now how much am I adding by? 8. Okay, now if this is 12, then it's a add of an add, meaning I added 4, now I add 8, now I add 12. Is this going to be adding 12? And that means it's not quadratic. Remember, quadratic means you're adding a same amount every time. So it would be like 4 to 8, 8 to 12, 12 to 16, so on. But that's not, so this must not be arithmetic at all. This must be, what's the other word? Geometric. Yeah, this is geometric. So if this is geometric, oh, I'm gonna switch colors. If it's geometric, then we have to find the base. How do you find the base? There you go. Change of y2 over change of y1. What is change of y2? And you divide that by 4. What's 8 divided by 4? The base is 2.
Wait, mister, I thought 16 to 32 was 16.
16 to 32 is 16. Just checking to make sure. I don't make mistakes, I just check you. That's all. Sorry, the base is 2. So do you remember the formula? Sorry, what type of function is this then?
Expo.
This is exponential. Exponential is when the y values are geometric. They're always one operation higher than the x column. Okay, so this is exponential. Now look at the values. Are they growing or are they decaying? Are they increasing or decreasing? They are growing. Okay, for exponentials, are exponentials, for concavity's sake, are they normal or are they backwards? They're normal. So if it's growing, this is concave up. Therefore, if it's concave up, what is true about its AROC? Its rate of change? It's increasing. Increasing is the word for AROC. And what would be true about its delta AROC? Okay, so just to make sure you remember what this is, delta AROC is change of y divided by change of x. Notice what's happening to each of these. This would become the AROC column because you're dividing by 1. AROC, you would divide that by 1. What's happening to my AROC values? They're increasing. And if you calculated the change between them, you would have positive numbers. Okay? We have to write an equation. I gave it to you the very first slide today. What is an exponential function's equation that you're going to use? You remember? This is what they're going to give you. And I said this is not as powerful. We're not going to use that one. What are we going to use instead? Y equals, instead of A, what do we put? Y1 times B, and then up here, I put it in parentheses just to make it match linear. X minus x1. That's what we're plugging into for exponentials. So we plug in our values here. We would have y equals, what's y1? 4 times the base. 2 to the power of x minus 1. That would be my equation there. You can manipulate equations just to know that. Just remember, you can always manipulate an exponential pretty easily using properties if you wanted to change your equation around. So that might not be the one you see on your test. You might have to manipulate it. For example, 4 could be rewritten as a base of 2. What is 4 in terms of base of 2? 4 as a base of 2. If I want to write as a base of 2, it has to be base with how many powers here? 2. And do you remember what you can do when you're multiplying by the same base? Multiplying by the same. Remember, y's on exponential are one operation higher. If you're multiplying the y values, that's the same thing as doing what to the x values? Adding. You could rewrite this as 2 to the power of x minus 1 plus 2, which is the same thing as 2 to the power of, what's negative 1 plus 2? Plus 1. You could rewrite that equation right there. Both of these would all, I mean, this, you could write the equation that way as well. Okay, so just know you can manipulate exponential equations. Okay. Yeah. All right. Are we good to go to the next one?
Yes.
All right, let's look at this table again. This time I try to make the numbers a little bit more complex. Let's see what's going on. When you take a look at this, what do you see the quickest? What are you finding right now? I hear plus 2, plus 4, plus 8. You're doing delta x. If we look at our delta x, we add 2. Then we add how much? 4. Okay, so I'm not adding the same amount, but it could still be arithmetic of an arithmetic, like a quadratic. If this goes 2, 4, 6, is the next one 6?
No.
It's not 6. How much is it?
8.
8. Okay, so this is not even quadratic. What's happening instead? This must not be arithmetic at all. It must be what type? And geometric. We're going to call this geometric over here. If it's geometric, how do you find your base?
Y2 over chain divided. Oh, x1.
Yeah, this time it's just the x's. Delta x2 divided by delta x1. What is delta x2?
4.
4. Oh man, I got the same base this time, don't I? Well, we have a base of 2 here. Okay, now tell me about the y, the delta y's, I should say. The delta y's.
It's plus 2. Arithmetic.
This is arithmetic. It's plus 2. Delta y is equal to positive 2. Therefore, this is arithmetic. By definition, what type of function is geometric in its x column and its y column is arithmetic? This is a logarithmic. Is it a logarithmic growth or decay? Look at the values. Are they increasing or are they decreasing? They are increasing. If it's logarithmic growth, what's true about its concavity? Logs are normal, logs are backwards. Backwards. If it's logarithmic growth, that means it is concave down. Not only is it concave down, if it's concave down, what has to be true about its rate of change? And what would then have to be true about the delta A rock? Okay, let's start writing an equation now. With an equation for a log, you're going to say a times log base. You could have an x value in here. I'm going to leave it blank for now. Where do I find the a value again? Your a is going to be delta y, which in this case is 2. So we're going to say y equals 2 times the log of, what's our base? 2. And I'm going to leave it as an open-ended x. We're going to see if this mathematically works. We might have to make an adjustment here. So if I go to plug in the numbers here, I'm going to just focus on the log. What does a log calculate again? Let me do it. The powers. We're going to calculate the powers here. How many powers of 2 does it take to get to be an x value of 3? That doesn't work, does it? Does 2 go into 3? This one we have to make an adjustment. We have to adjust our values. Now I'm looking over here. I know 2 goes into these numbers because let's just make 3 become a 2. How do I make 3 become a 2? Okay, let's play around if it's a -1. Let's see what we would get. Okay, what if it was 3 minus 1? We're going to experiment for a moment. We're going to see, what if this is the equation? What is 3 minus 1? 2. That would be log 2 of 2. How many powers of 2 does it take to get to 2?
1.
1. Okay, that would be 1. So 2 times 1 would give me 2. Now, is that what it's supposed to equal there? No, and I'm looking at this one. It might even be, let's try one more. It might even be we have an addition on the outside. This one might be tricky. Let's try one more. I'm going to plug in 5. We're going to go with the theory we need to subtract 1. Okay, if we subtract 1, and the reason I'm choosing that is just because I saw this number 2 there. If I subtract 1, what do I get? 4, which is still good over here. How many powers of 4 does it take to get, how many powers of 2 does it take to get to 4? 2. So we'd be saying 2 times 2. What's 2 times 2?
4.
4. Okay, originally we had 2 times 2 and we got 2. This time we did 2 times 2 and we got 4. How do I make that equal 5? Add 3. Now, what happens if I add 3 here? 7. Okay, so here's the equation. It's going to be like this plus 3. That's going to be the equation. Now, that one's a little tricky. That one was a little tricky, but that would be our equation this time. I'll plug in one more. I just want to make sure you understand how logs work. I'm going to plug in one more just to keep checking it. But I think this will work like this. Let's do the next log. We know it's log base 2. That part we know. And we know we're going to multiply by 2. Let's plug in the next value. What's the next value they give us? 9. When I plug in a 9, I need to subtract 1, which is, this is looking good because it's going to equal that number there. What is 9 minus 1?
8.
So now you're asking yourself, how many powers of 2 does it take to get to 8? Nope, not 4. That's dividing. 3. It takes 3. So we'd get a 3 there. Okay, so it's 2 times 3. What's 2 times 3? 6. What do I need to do to 6 to make it a 9? Yeah, see how that worked? Okay, so that's why those values work there. And these, we needed to subtract 1. We needed to subtract 1 each time to make it the AROC column. That's why I went with the -1 originally, just so you know. That's why I did that. I guess I never did these two, so I won't write them on those. Okay. Now that's kind of some higher level there. Let's try one more, and then I'll have 2 that you can kind of practice on. All right, let's take a look. Have I done 3? Is that right? 1, 2, 3. Yeah, I've done 3. Let's try this one more time here. What do you notice as you take a look at this? Delta x all the way down is adding by 1. Okay, if it's adding by 1, is it arithmetic or geometric? What do you know right now this cannot be? What type of function can it not be? It absolutely cannot be logarithmic, because logarithmic has to be geometric there. Okay, how about delta y here? We add by 10. What about here? 30. Okay, if it's quadratic, we'll be adding to the adding the same amount. So it'll be like 10, 30, 50, 70, 90, so on. If it's quadratic. Is this going to be quadratic? It's absolutely not quadratic. How much do I have to add from 45 to 35? 135? How about 90? Is that 90? Yeah, and if you want the next one, this would be 270. So are we saying this is arithmetic or geometric? Geometric. Whoops. So by definition, if the x column is arithmetic and the y value is geometric, what type of function is it? Exponential. Is our data growing or decaying? Is it getting, are the y's in particular increasing or decreasing? Therefore, it is exponential growth. And because it's exponential growth, exponentials are they normal or backwards? Normal. So this would be concave up. And if a function's concave up, unbreakable chain, what's true about its, whoops, I skipped one. What's true about its AROC, its rate of change? It's going to increase. Notice the column, it is increasing. That's increasing. And what about its delta A rock? Perfect. You got that part down, it sounds like. Now let's come over here to find your base. If it's geometric, you have a base. How do you find your base?
Y2 over Y.
You got it. Which in this case would be 30 divided by 10. What is 30 divided by 10? Sweet. So for exponentials, remember how delta math always says this. Is that the function we're going to use?
No.
What are we going to do instead? I want to put that in parentheses just so it seems a lot more like the linear point slope formula as well. All right, let's plug in and be done. Y equals, what's our Y1?
5.
5. Y1 is 5 times, what's our base? 3 raised to the power of x minus, in this case, 2. So we're saying that's going to be the answer. Let's double check. Let's plug in our numbers. If I wanted to plug in the first x value, and I have 5 times 3 raised to the power of 2 minus 2. What is 2 minus 2? What's anything to the power of 0? What's 5 times 1? Is that good?
Yeah.
Is that what it's supposed to be? All right, that looks good. Let's try the second one. It would be 5 times 3 raised to the power of 3 minus 2. That would be 5 times 3 to the power of 1. What is 5 times 3? Is that what it's supposed to be? Yeah, those are looking good. Those are looking good. So we got our equation there. Questions over that? All right, I have, let's see here. Is it 1 or 2 more? 2 more? And these you can try on your own. I'm gonna let you try these on your own and see what you come up with. Is that okay? I'll let you try a couple on your own. Yeah, go ahead. All right, here's the first one I want you to try. If you watch the video, just pause it, try it. And then the second you're gonna look at is here. So I'll pause it here. All right, let's move on. So those two are up there for you to practice on your own. Let's switch gears entirely. Let's start doing some properties here, okay? So there are some properties. There's 3 properties that we had with exponentials and logarithms. Product property, quotient property, power property. We had all 3 properties. How those tables work out the arithmetic and geometric relationship. You can follow using that idea that the geometric is one operation higher. You can figure out how the properties work. Now, logarithms also have an interesting one called the change base. And that's what's going to happen here. It says here, what is this right here? Natural log, which means a log with a base of e. If log of base of e, natural log natural a equals 2, and log natural b equals 3, evaluate log b a to the 5th. Well, here's the problem. Did they give us anything that was log with a base of b? So we need to do a change of base. So here on this one, I want you to write, why did I do that? Let's try this again. Log base b of a to the 5th. This is equal to, using properties, I want to remind you of a couple things. Number 1, you can do something with a power. You have a power property. So just remember the relationship for exponentials and for logarithms. That one table of values is arithmetic, one value is geometric. On a logarithm, which one is arithmetic, which one's geometric? The x's are geometric. What did that mean about the y's? Okay, here's how that plays out here. That means they're one operation apart. So this power right now, is the power on the log, or is the power on the inside, which we would call an x value? Yeah, and I should have a parenthesis around that. Go ahead and put a parenthesis there. There should be one there. AP Classroom would give you one. So I'm going to go ahead and sneak in the parenthesis here. This 5th power is on the inside. So That means geometric, that means it's one operation higher. If you have a power here, what is one operation lower than a power? It's multiply. It's the same thing as multiplying your logarithm. So this 5 can be moved as a multiplication of the logarithm. 5 log base b of a. Now I don't need the parenthesis because it's just a by itself. Does everybody follow what just happened there? The 5 was powering. What's it doing now? It's now multiplying. Just going to do a red dot so you can stand out a little bit. Good? Okay, we're getting closer to our answer. Now, here's the problem. We have the wrong base. What's the base supposed to be up here? If it's a natural log, what's the base on a natural log? E. That's the same thing as log base E of A equaling 2 and log base E of base equaling 3. Okay, now that we know that, we have to change the base. There is a change of base property. The change of base property means this. You can change the base anytime you want to. How you change your base is like this. We still have this full 5 that's multiplying. You write it as 2 logs, where the original base becomes the number that's getting logged in the denominator. The original number that's being logged is the value that gets logged up in the numerator. Now, we can pick any base whatsoever we want this to be. What base on this problem should we choose it to be? What base was it originally up here? No, it wasn't 2. What was our base originally? What base was it originally up at the, did they give us up at the top? E. So I'm going to choose to have a base of E. So when you do a change of base, you get to pick whatever base you want. You just need to remember the base itself becomes the log that's dividing. The original log, the value that was being logged originally, that becomes the log in the numerator. Now that's called change of base. That right there, what I did is this is the change of base property. That's what that is. That's the change of base property. The first one was the power property. Okay, now that I have that, I can substitute. We know log E of A is the same thing as natural log A. And the denominator log E is natural log of B. So I can just rewrite that. And now I can substitute. What is the natural log of A? Look up here. What is the natural log of A? What's the natural log of B? And so my answer is going to be, what's 5 times 2? You multiply the numerator. When you multiply the numerator. That's dividing. So it's going to be 10 divided by 3. There's your answer. 10 divided by 3 is your solution on this problem. That was a substitution there. I can write that in there. Substitution. This was just a rewrite. Okay. I think I have another one of these so you can see this again to figure out what's happening. If log 3a is 2 and log 9b is 3, evaluate log 27 ab to the negative 2. Oh my goodness, what's going on this time? All right, let's start with, we have log base 27. Again, this should be in parentheses. That's my fault. I'm going to go ahead and put that in parentheses now. ab to the negative 2. All right, to break this apart, the first thing you need to notice is this negative 2. Does the negative 2 power both A and B? No. What is the negative 2 powering? B. So we first have to break apart A and B. What are A and B doing to each other? Are they adding, subtracting, multiplying, or dividing? Multiplying. Okay, if you have a log that's multiplying on the inside, If you have a log that is multiplying on the inside is the x value. If you're multiplying on the inside for a log, is it on a log, is x arithmetic or geometric? No,
Yeah.
it's geometric. So if this is geometric, that means it's one operation higher than this side. So this side's one higher. What is one less than? Multiplying. What's one operation less than?
Divide.
Adding. No, it's adding. Divide would be the opposite. One less would be adding. We can change this log that's multiplying into two logs that are adding. This is called the product property. Log 27 of A plus log 27 of B to the negative 2. That would need a parenthesis because that's more than one value. Okay, we're going to say that is called the product property. That's what we did there. The product property. Just so you can follow along what I'm doing. Okay, what do you think we could do now? Any other properties you see? Ah, good. We have a power here. What can I do with that power? Yeah, that can become a multiplication in the front. So if you are powering on the inside, if you have a power on the inside, again, the log is geometric, so that means it's one operation higher. What's one operation less than a power? Multiply. So we can make this power multiply in the front. So this is going to equal log A 27. Nothing happens on that one. Log base 27 of A. I'm going to multiply by a negative 2. Do I need a plus a negative 2? No, I can just write that as minus 2 log, and that 2 is multiplying there, log 27 of B. Is everybody tracking so far?
Mhm.
That's now multiplying right there. Okay, the last thing to get my answer, I'm getting really close. This is log 27 of A. This is log 3 of A. This is log 27B. This is log 9 of B. You know what I need to do last? Not a quotient. We need to change the base. That's what we need to do, change your base. So the formula to change a base. Here, I'm just going to do this. My colors aren't cooperating with me today. I don't know what's going on. I'm going to change the base here. And I'm running out of space. So I'm going to do it down here. Change base. If you want to change your base on a logarithm at any point, you can. Do you remember how to change the base? You have log divided by log. What goes to the numerator this time? A. What goes to the denominator? Not B. Nope. You're looking at just this log right there. 27. Good. We're going to pick a base in a moment. But I'm going to continue on minus 2 times. And I'm going to do it here again. We need to change this base. So I'm going to do log B divided by log 27. Okay, on the first log, you can choose any base you want. What base would be smart to choose? What's on the A, what's the base right there? 3. We're going to choose a 3. Okay, what about on the log that has the B? 9. I want to choose a 9. And now we can start evaluating. Log 3a. Log 3a, we can actually substitute that. What is log 3a? That's going to be 2. This log 327. Remember, a log calculates powers. Log 327. How many powers of 3 does it take to get to 27? 3. That's 2/3. Minus 2 times. What's log 9b? 3. And now log 927. This one isn't going to be quite as easy to calculate. I'm going to do an upside down division for this. Log 927. Since 9 does not go in an even number of powers, I'm going to do upside down division. 27. 9 goes into 27 how many times? 3. But the problem is those aren't the same number, so you have to break this down. 3 goes into 9 how many times? Okay, so here's what that means. 27 is 3 powers of 3. 27 is 3 powers of 3. But 9 is how many powers of 3? 2. That's 3 halves. Okay, this, when we simplify, will give us our answer. All right, 2/3 minus 2 times 3. Yeah, so it's going to be, goodness, I'm so running out of space here. I don't know if I can sneak that in. This will equal, here, I'm just going to write it right there. 2/3 minus 2 times 3 is 6. Do you know what you do when you're dividing by another fraction? You multiply times its reciprocal. What's 6 times 2?
12.
That would be -12. Divide that by 3. Actually, I'm not gonna divide by 3 because I'll have a common. I will have a common denominator if I don't. So this is 2/3 minus. What did you say 6 times 2 was? 12/3. 2/3 minus 12/3 is. What's 2 minus 12? -10/3. That's our answer this time. Goodness, I got tricky there running out of space. All right. Let's switch gears. I don't want to spend too much time on something that it's not the majority of what we did. I just want to show you properties, how things work with logs in particular, that you can change the base at any time. All right. When you see a graph that looks like this, what type of plot is that? Do you remember? Semi-log plot. Very good. It's a semi-log plot. Semi-log. Now, why did they call it a semi-log? Because you don't log the whole graph. You log half of it. Semi means half. What half gets logged? The y. What's happening is you log the y. Remember, what algebra occurs for the data to be placed on the graph? You log the y values. You log your y values. That's what happens. So remember that these lines aren't counting by like ones. They're not counting by tens. They're not counting by hundreds or 20s or 30s. What are we actually counting by? Powers. And so come over here. But that's 10 to the 0 power. This is 10 to the first power. This is 10 to the second power. This is 10 to the third power. If it is semi-log, I have seen other people not even write the numbers 1, 10, 1,000. I've seen some do it where they actually might write the number 1. They might write the number 0. Then they might write the number 1. Then they might write the number 2, number 3. Now, if you did it this way, you would have to say this is a semi-log y. They would have to, whoops, got dyslexic. They would have to say it's a semi-log of y if they did it that way, but they could do it that way. But what are these numbers actually representing? Are they not representing the actual number 0, 1, 2, and 3? No, what are they actually representing? The powers. Okay, but if they don't show you semi-log y, they will not do that. They would have to say that. They would have to say semi-log, which they usually don't say the word semi-log. And so that's where they get those values, okay? Make sense? When do I do a semi-log? This is the question for you. When do I use a semi-log? Do y'all remember? It's when the data is exponential. You do a semi-log when the data is exponential. What will it make? How about this? The semi-log will make the exponential appear linear. Okay. So when do we use a semi-log? When the data is exponential, and only when it's exponential. What will it do to it? It will make it appear linear. Is it actually linear though? No. What is it actually? Exponential. Okay, good. Okay, so let's take a look at this example here. Graph the equation y equals 2 times 4 raised to the power x in the grid shown. What type of function represents the appearance of this graph? Okay, so if I wanted to plot those points, let's just get a little table going here to help us plot it. And then I will show you the equation here in a moment. All right, let's plot when the x value is 0. The x value is 0. Plug in a 0 there. What is 4 to the 0 power? Anything to the 0 power is 1. What's 2 times 1? 2. Okay, so at 0 we have the point 2. Remember, on the y's it looks like it starts at 1, so that's a 1. That means 2 is the next mark. Put a dot right there. There's our first point. Now we're going to plot a point at when x is 1. Okay, so these are my x values. These are my y values over here. Let's plot an x value of 1. When x is 1, what's 4 to the first? 4. So 2 times 4 is... So when we have an x of 1, we should have a y value of 8. So go to 1. Now remember, when you count, this is ones now. So we're counting by ones. Technically, we're counting by powers. But these marks from here to here are representing increments of 1. So it goes 1, 2, 3, 4, 5, 6, 7, 8 right there. Put that point there. Okay, so that's the point 0, 2. This is the point 1, comma 8. Everybody tracking with me? Okay, now 2. This is exponential, so you should figure out the pattern real quick. Exponential, remember it's arithmetic over here, and what's happening on this side? Geometric. So we should be multiplying by 4. Let's just check it. 4 squared is 16. What's 2 times 16? 32. So what's happening each time to my number? It's being multiplied by 4. So this goes to 32. So at 2, we're at 32. So this is 10. So from here to here, we're now counting in increments of 10. So 10, 20, 30, go just a little bit above 30. Put a dot. That is 2, comma 32. Everybody following along? Okay. Use your ID badge. We just said a semi-log makes exponential look or appear what? Okay. I'm going to draw a line all the way across. Exponential should appear linear. Okay, that means the next value. I'm just going to go fast here rather than telling you. If you multiplied this by 4, you would get 128. So when I go to 3, I should be at 128. Now this is 3, and it should be 128. Now why is that the case? Because once you get to 100, it's counting by increments of 100. So that's 3, comma 128. If I were to multiply again by 4, this will be 512, I believe, if I'm doing my math right. I hope I'm doing my math right. That should be 512. Let's check the point over here. This is 100, 200, 300, 400, 500. It looks like I'm getting a little too tall, a little too fast. Let me just make my line go down a little bit. There we go. That would actually be 5, not 5, I'm sorry, 4, 5, 12, and so on. That's how it should work. Is this actually linear? Is it actually the keyword? Is actually linear? What is it actually? Exponential. How does it appear? Linear. The equation of the linear appearance is this. If you remember how this is exponential, let's just make this very clear. The exponential function is y equals 2 times 4 to the power of x. The linear appearance, what you do is you take a log of both sides. You take a log of the y, ultimately, like a log of the outside. It would be log y equals log, and this already has a parenthesis, so I'm going to use a bracket. 2 times 4 to the power of x. We don't have time to spend too much on properties here, so I'm just going to call them out. What happens when you multiply in the inside of a logarithm? Outside add, so it becomes a log 2 plus log 4. And then what can I do with that power of it? Well, I'll put the power on it first. It can multiply. And because I wanted this to look like a line, I'm going to move it to the front and I'm going to say this is equal to log. Notice I'm going to go out of order here. 4. And I want to put the multiplying x on the outside plus log 2. This is the appearance of slope. This would be the y-intercept. Notice, where was our y-intercept? What's the y value of the intercept? 2. What do I have here? Log 2. The difference with the slope is we're actually multiplying by 4 all the way. See how it goes 2, 8, 32, whatever? It's not rise over run on the semi-log because you're actually multiplying by it. So I'd be multiplying by 4 the whole way. Does that make sense? That's how it always plays out. The base becomes the slope. What becomes the slope?
Base.
Base has the appearance of slope. And what has the appearance of the y-intercept would be the a value or the y1 value, whatever you want to call it. That would be your y-intercept. Okay? Is that it for semi-logs? Yes. Let's review some compositions here. It says that g of x equals log 9 of f of x. And g of x equals this. What is f of x? So good old-fashioned algebra here. Let's finish up with some good old-fashioned algebra. If I want to solve, what could I do first here if I'm trying to solve for it? It says, what is f of x? That's what I'm trying to solve for. I'm trying to solve for this f of x. How could I begin this problem? Well, how can I solve this for f of x? Before I go anywhere else, I need to do something with these two equations. What can I do with them? Someone say substitute. I can substitute. What can I substitute? Look closely. G of x is shared. This g of x can be replaced. What can g of x be replaced with? Instead of this g of x, it can be replaced with?
0.5.
There you go. We're going to substitute this in. So instead of g of x, I'm going to say 0.5x plus 2 equals log 9 of f of x. How do you solve that from there? We're trying to solve for f of x. How do I get f of x isolated? We're going to exponentiate by 9. If I exponentiate both sides by 9, what happens to log 9, 9? 9 log 9, I meant to say, becomes a multiplying 1. And so we have 9 to the power of 0.5x plus 2 equals f of x. Okay, we have our answer. Is this in the right form? No, it's not yet. You see how that's not the same form? So now that I know what f of x is, I need to get it into this form. So I can do a property here. Okay, so I'm going to do a property. Now that I know what f of x is, I'm going to do a property. What can I do with exponentials that are the exponents are adding? multiplying. So it's going to be 9 to the power of 0.5x plus, not plus, I'm sorry. You said bases that are multiplying. If the x's are adding, you can make the y's multiply. Are you good with that? Where'd the plus go? Where'd the addition of 2 go? It became a multiplying of base with a power of 2. Did everybody follow what's happened there? Now I've almost got it in the correct form. Getting close. Also, I didn't do this. Power to a power. Well, I'll just do it in the next step. Now what I can do, when I have power to a power, I can do 9 to the power of 0.5 raised to an x. If your x's are multiplying, you can raise that to a power like that. Times, do y'all know what 9 squared is? 81. Okay, a 0.5 power, that's the same thing as a square root. What's the square root of 9? 3. That's 3 to the power of x times 81. I now have it in the right form. F of x equals, I'm going to put a first, 81 times 3 to the power of x. There's your answer right there. 9 to the 0.5 is equal to the square root of 9. 0.5 is the same thing as a square root. That was kind of the key there. All right. How do we find an inverse? Switch x and y. So what represents y in this problem? F of x. So if this is a y, the first step, you would switch x and y. Solve, and now after you switch x and y, to solve for an inverse, you solve for your y. We need to now solve for this y. What would you do first? We add 3 on both sides. Good. So when I add 3, I have x plus 3 equals 2 times 4 raised to the power of y minus 2. Now what? We're trying to get the y by itself. What do I get rid of now? What's on the most on the outside? I can't add 2 because that's in a power. Divide by 2. That 2 is multiplying, so let's divide both sides by 2. So x plus 3 over 2. Okay, so that would equal 4 raised to the power of y minus 2. We're almost there. Now what? What's the opposite of exponentiating by 4? Let's log both sides by 4. All right, so we log 4 both sides. Whoops. We log 4 both sides. Now what happens when you log 4 of 4? And power property, those multiply. So that's going to be y minus 2 on this side. And so we're now at our last step. Our very last step says we will do what? What we do to get y all isolated by itself?
Add 2.
You add 2. And like that, we have our inverse. So I'm not going to write it as y equals. I'm actually going to write it as f negative 1. What does f negative 1 mean? The inverse of f would be log base 4. That addition of 2 does not go on the inside. It would be x plus 3 divided by 2 all, and then add 2 on the outside, just like that. All right, let's take a look at this one. What is the inverse of the function g of x here? How do we find an inverse again? Okay, so instead of g of x, instead of g of x, what will we write instead? Okay, so the inverse would be 5 equals, x equals 5 times the log 7 of 3y plus 1 minus 2. That's the implicit version of the inverse. That is the inverse. Will that be an answer choice though on the test? No, because what do you need to do that? You need to solve for the y. What would be our first step here solving for y? We add 2 to both sides. So when we add 2, we have x plus 2 equals 5 log 7 of 3y plus 1. Now what? Get rid of the 5? How do I get rid of the 5? Oh, no, the 5 is multiplying. So we divide everything by 5. And so we have x plus 2 over 5 equals log 7 of 3y plus 1. Okay, getting closer. Now what? Exponentiate. Very good. It's right now it's being logged by 7, so we exponentiate by 7. Okay, what's going to happen when you 7 log 7? That's just going to become 1 times. So we're going to have 7 to the power of x plus 2 divided by 5 is going to equal 3y plus 1. My goodness, run out of space here. Next step, we subtract 1 from both sides. Will this 1 subtract from the 7? No, it won't. So 7 to the power of x plus 2 over 5 minus 1 equals 3y. Last step was our very last thing here. We divide that by 3, and finally we'll have our answer. Y will be isolated. Everything gets divided by 3 when you divide. So they called this one g, so I'm going to call it g negative 1, meaning the inverse of g would equal, it's going to be all this divided by 3, 7 to the power of x plus 2 over 5 minus 1. That would be my answer right there. Question about domain. When we get to domain, do you remember what the rule is on domain for logs? There are 3 rules of domain. You can see them up there in the wall. Cannot divide by 0. You can't have a negative root. Logs cannot be a non-positive number, meaning it has to be positive. So to solve the domain, you would just take the inside and say it has to be positive. Mathematically, how do you say something has to be positive?
Linear.
Oh. Greater than 0. The way you would solve that is you would say 3x plus 1 must be greater than 0. That's how you'd solve that. What would you do first? So I'm going. You would add subtract 1 from both sides. So 3x would have to be greater than negative 1. Last step. Divide by 3. This is saying x has to be greater than greater than negative 1/3. Said another way, you could say it's the numbers from negative 1/3. I'm doing a parenthesis because it's not equal to, all the way up to infinity. Any numbers that are greater than 1/3. That's how you can write your answer, either form, like that. All right, so now let's take a look at a more difficult domain question here. What if we were doing the domain of this function? Well, again, with domain, there are 3 functions that are limited or restricted in their domain, and a log is one of them. A logarithm, by rule, the values inside the logarithm must be positive. They cannot be a non-positive number. So that means they cannot be 0, they cannot be negative. They have to be greater than 0. So the way you'd go about solving this is to say 3x squared plus 2x minus 5 has to be greater than 0. The key here is to identify that this is in a quadratic form. That is a quadratic expression inside this logarithm, and so the way to solve a quadratic is to x method. At least in my opinion, the easiest way is to do an x method on this. So 3 times negative 5 is negative 15. Your b value is 2, and so you'd go through the factors of 15. The factors of 15, we have 1 times 15. Positive and negative, you would have 3 times 5. Those are the only 2 sets. You would need those to somehow have a sum of 2. So my values would have to be not the 1 and the 15, they have to be the 3 and the 5. To make it be a sum of positive 2, we have to have a negative 3. 5 minus 3 is 2. So what do I do now? Since my a term is 3, this is the value gets divided by 3, not this one. Remember what you do is on the a term, you cannot have the a term written twice. It's not going to be 3x times another 3x. That would equal 9x squared. It's got to be a 3x and an x. So 3x times x generates the 3x squared. Since this value can be divided by 3, that becomes the second term in this parentheses here. The one that the value, this one got divided by 3, so this would also get this negative 1. Like that. This 5, 3 cannot go into 5. So it goes with the 3x here. So this is plus 5 greater than 0. So these are my two factors. Since I'm going to use the zero product property, it states that if you're multiplying, you get a product of 0. The only way to do so is that each factor must individually be 0. So what we're going to look at here is this would have a 0 if you consider a graph in a second, where you would add subtract the 5 across. So negative 5 and then divide by 3. This has a 0 at negative 5/3. This has a 0 at positive 1. And so when I put that together as a graph, again, we're taking the area at the interval where the graph is greater than 0, the values. Negative 5/3 is almost negative 2. So there's negative 1, there's negative 2, that's negative 1, this is negative 2. Negative 5/3 is almost negative 2, it's somewhere in here. And then over here on this side of the graph, here will be positive 1. And again, we'll have a second 0 there. This is a parabola. Not only is it a parabola, it's positive, so this should be an upward facing parabola, concave up parabola, like this. And so the intervals where this parabola is greater than 0 are the x values, not in between. Those are the values where it's not true. It's the x values outside the window. So the values over here and the values over there. So what that means is we have solutions when x is less than negative 5/3. When x is less than negative 5/3, we'll have a solution area. And when x is greater than 1. When x is greater than 1, this is the x-axis here. So x is greater than 1, x is less than 5/3. That would be our solution set. And so you could write it as an or statement. X is less than negative 5/3, or x is greater than 1. You could write it as inequalities. This would be from, this is inequalities. I could write it as an interval notation. It goes from negative infinity to negative 5/3. And since we have to be greater than 0, it's a parenthesis union. X starting at 1, but not including 1, to infinity. You could write your answers in either form there. Okay, so that's how we do domain, especially with a quadratic expression inside the logarithm. And finally, let's wrap it up with this. If f of x equals log 3 x plus 3 minus log 3 x minus 2, and g of x equals log 3 the expression x minus 5, for what values of x does f of x equals g of x? To solve this, we need to substitute. So I am solving for when f of x equals g of x. The first substitution I'm going to make is, what in the world is f of x? Well, f of x is set up here. It is log base 3 of x plus 3 minus log base 3 of x minus 2. And g of x, this will equal, let me slide this down so it's lined up. G of x, I'll represent here in red. G of x is here, that is this log 3 of x minus 5. So I've substituted. Okay, I substituted for the f of x, I've substituted for the g of x. Now these are set equal to each other. And so to solve this, I need to first, to solve with logarithms, you have to isolate the logarithms on each side of the equation, which means these two logarithms need to become 1. I'm subtracting 2 logarithms. We did this earlier, but if you subtract 2 logarithms, if you are subtracting 2 logarithms, in this case the base is 3. If you have 2 logs that are subtracting one another, because a logarithm is geometric arithmetic, this is one operation less. So if this is subtraction, this needs to be division on the inside. what I can do is I can take these two and use the quotient property and make this become log base 3 of, I'm going to go a bracket here, the expression x plus 3 over x minus 2. I don't need a bracket. I took away the other parentheses. I'll just leave it as normal parenthesis like that. Equals log base 3 of x minus 5. That right there was the quotient property. Now from here, they're both isolated, both logarithms are isolated, so to get rid of this is called the one-to-one property, but basically what I'm going to do is I'm going to exponentiate both sides by 3. Let me use a different color I haven't really used yet. If I exponentiate both sides by 3, the 3 logs 3, those cancel, these cancel, and so we're left with x plus 3 over x minus 2 is equal to x minus 5. And what I'm going to do now to solve is I'm going to get rid of this rational expression over here, the division. I'm going to multiply by x minus 2, and I have to multiply by the factor x minus 2 to make sure they cancel out. So this will get multiplied by x minus 2. We have to distribute, that's what will happen there. Those cancel out, and so we have x plus 3 equals, and I will box method this out here. I'm multiplying x minus 5 times x minus 2. And you'll see we get x squared minus 5x. When I multiply, I'm distributing all the way through, minus 2x, and then plus 10. Negative 2 times negative 5 is a positive 10. So I combine my like terms. I have x squared minus 5x minus 2 more x's, that's minus 7x plus 10. So I got those values by coming over here, and then I'm coming right back just to track with how I got those values. Now to solve a quadratic, what you do is you set it equal to 0, and we're going to do this zero product property like earlier, like the last problem. So I set this equal to 0, and now I have 0 equals negative 8x minus 7x minus 1 more x is minus 8x, and this becomes a positive 7. And I can do the zero product property. It's set to 0. I have a power. Zero product property means if I factor this into products, what I can do is, I'm at the 0, but not the product right now. I can solve for each value of x. It could be potentially an answer. A times c over b. My factor here, my a is 1, so 1 times 7 is 7. My b is negative 8. So the factors of 7, the only option we have is 1 and 7. To make them have a sum of negative 8, they both need to be negative. So negative 1 and negative 7. Again, split my a value, and we'd say 0 is going to equal x minus 1 times x minus 7. Therefore, using the zero product property, x is equal to 1 or x is equal to 7. Now, check your answers. Remember with logarithms, this is tricky because there can be a domain issue. So this one would say allowable answers. All logarithms must be possible. So this would be the restriction here is that this would say that all x values must be greater than negative 3. Which, so far so good. Both those answers, whoops, where are they? 1 and 7 are both greater than negative 3, so we're good. When I check the next logarithm though, this restriction on the second logarithm, for this logarithm to be defined, is that x has got to be greater than positive 2. Well, this answer is now out. That must be extraneous. That is outside the domain. And I didn't even check the last one. What's our last restriction? Let me go back up. Here, my restriction, oops, let me go red. My restriction on this logarithm is that x actually has to be larger than 5. Otherwise, that logarithm would not be defined. And so all answers must be greater than 5. Therefore, the only good answer here is 7. 7 is our only good answer. You could plug that in the calculator to check, but this is true. Log 3, 7 plus 3, that's 10. Minus log 3, 7 minus 2 is 5. You could divide that. 10 divided by 5 is 2. So log 3(2) is equal to, put in the 7 here, 7 minus 5 is 2. Log 3(2) equals log 3(2). Works out. That's our answer. And that's a wrap.